Stanford University.
The subject this quarter is a collection of things, but mostly special relativity and field theory. We're coming back now, not quantum field theory. We're not prepared for quantum field theory yet. We've learned classical mechanics, those who have participated up till now. Classical mechanics, the general structure of classical mechanics, what it is, how it works, the action principle, Hamiltonians, Lagrangians, all that kind of stuff. And I assume you know it. We also learned some elements of quantum mechanics. I can't believe I taught a whole quarter on quantum mechanics and we never got to the harmonic oscillator. That's when I tell people that, they say, "What did you do?" And I tell them, and they say, "Oh, that's good." But we learned the principles of quantum mechanics, but we didn't spend much time on examples. In order to go forward with quantum mechanics and quantum field theory, we're going to have to do some more quantum mechanics for sure, but not this quarter. No quantum mechanics this quarter. We're back to classical physics, but now back to the relativistic end of things. We've studied non-relativistic mechanics, motion of particles, mostly motion of particles, F equals ma, Newtonian physics. We have not studied anything about light, and that's because light basically is a relativistic phenomenon, a phenomenon that has to do with special theory of relativity. And that's going to be our goal this quarter, the special theory of relativity and classical field theory. Classical field theory means electromagnetic theory, basically electromagnetic theory, waves, forces on charged particles, all that sort of thing. But in the context, very definitely in the context of the special theory of relativity. So that's where we're going to begin. Special relativity, that's tonight. I suspect that most of you have at some point in your lives learned the elements of special relativity. How many people would not fall into that category? So I'm right then. Just about everybody has learned special theory of relativity. How many people feel that I could completely dispense with it without losing any, do you feel that you would like to go through special relativity? All right, so I'm getting the rough answer that the answer is yes, and that's what I had prepared to do tonight. But I had also been prepared that if everybody said we really understand special relativity completely, can you move on to the next thing? I would have said yes. But I'm glad you didn't, because I like the idea of teaching from the beginning. Okay, so let's come to special relativity. Let's first talk about relativity. Well, let's even go back a step before relativity, the idea of a reference frame. The idea of a reference frame, you know what, I'm not going to spend a lot of time on the basic philosophy and everything. You know what a reference frame is. We talked about reference frames in classical mechanics. It's a set of spatial coordinates, x, y, and z, usually based on Cartesian coordinates. To specify the coordinates, you will want to specify where the origin of coordinates is. There's ambiguity in that. You can translate it from one place to another. And you will also want to specify the orientation of the coordinates. In other words, by orientation, I mean they're free up to some rotation. You want to pick the x-axis that way, the y-axis that way, the z-axis that way, or change it, but specify it to begin with. And that's part of picking a reference frame, a spatial set of coordinates. In addition to a set of coordinates, which could be measured by meter sticks, if you like, if you want to think physically or concretely about what a coordinate system means, think of space as filled up with a lattice of meter sticks, so that every point in space can be specified as a certain number of meters to the left, certain number of meters up, certain number of meters in and out. And that's a coordinate system for space. And in order also to specify when something happens, not just where it happens, you have to specify a time coordinate. So a full coordinate system or a full reference frame consists of an x, a y, and a z, and a t. In other words, a time axis. And that's a reference frame. Now you can have different reference frames. Apart from the ability to rotate from one thing to another, you can also consider moving reference frames that are moving relative to some specific reference frame. We could speak of our reference frame. By our, I mean yours and mine. Now let me not say yours and mine, your reference frame. You're sitting still. I will assume that for the most part you will continue to sit still tonight. But I will move around from time to time. I may march past you like this, or I may march past you like that. And we will, if I think of my coordinates as a coordinate frame, a set of meter sticks that I carry with me and move with me as I move, so that at every instant I personally am at the center of my own coordinates, then my coordinates are different than your coordinates. You will specify an event by an x, y, z, and t. I will specify it by a different set of x, y, z's, and t's to account for the fact that I may be moving past you. In particular, we won't agree about the x's. If I'm moving along the x-axis relative to you, my nose, I will always say, relative to me, is 6 inches in front of my face. I think it's probably less than that. And I will say my nose is at x equals 6. You will say my nose is not at x equals 6. You will say my nose is moving and it's at some position that changes with time, and so you'll give a different coordinate to it. In ordinary pre-relativistic physics, we will also specify times. Pre-special relativistic physics, we will also specify times, and in pre-relativistic physics, we would assume that we all have watches. Our watches are synchronized. We go through some operation to synchronize them. We'll talk about operations to synchronize watches, but we'll assume they're synchronized so that at a given instant of time, all of your watches agree with each other, and they agree with my watch. My watch agrees with your watch. That was an assumption that was made in all of pre-relativistic physics, that time is time is time is time, and there's no ambiguity associated with moving reference frames about what the time is at a given instant. What does relativity mean? Relativity means that for all coordinate systems which are related to each other by uniform velocity, all reference frames related to each other by uniform motion, the laws of physics are the same. The laws of physics are the same in every reference frame. The word is inertial reference frame. You know the term inertial reference frame. If one frame is inertial, then any frame moving with uniform velocity relative to it is inertial. What is an inertial reference frame? What is the first inertial reference frame that you start with? Let's just make it simple and say it's a frame of reference in which Newton's laws are correct, and in particular, where particles which have no forces on them move with uniform velocity. That's a reference frame. Every frame moving uniformly relative to it, not rotating relative to it, not accelerating relative to it, is another inertial frame. And it's a feature of Newtonian mechanics that the laws of physics, F equals ma, that together with Newton's law of attraction or Coulomb's law of attraction, they're the same in every reference frame. So if you like, the way I like to describe this is, go to the proverbial railroad train moving down the x-axis with uniform velocity, and think about you or me. I'm in the train, you're standing still. You have a set of laws, and the way I like to think about it is laws of juggling. Juggling is a good thing that makes a lot of use of classical mechanics, inertia, forces, all the good stuff. And if you know how to juggle at rest, you juggle exactly the same way in the moving reference frame. You cannot tell. Another way to say it is if you're in a moving reference frame, if I'm in a moving reference frame and everything is sealed so that I can't see outside, I cannot tell that I'm moving. I try to find out by doing some juggling, and I find out that my standard laws of juggling work, and I assume, therefore, that I'm at rest. But that's not right. All it tells me is that I'm in uniform motion. So the principle of relativity is that the laws of physics are the same in every reference frame. That principle existed before Einstein. It was not invented by Einstein. Sometimes it's attributed to Galileo. I don't know if he said it or not. Newton would have recognized it. And it is called the principle of relativity. What did Einstein add? Einstein added one law of physics. The law of physics is that the speed of light is the speed of light, c, that the speed of light is 186,000 miles per second, or that the speed of light is 3 times 10 to the 8 meters per second. That's a law of physics. Now, if you combine the two things together, that the laws of physics are the same in every reference frame, and that it's a law of physics that light moves with a certain velocity, you come to the conclusion that light must move with the same velocity in every reference frame. Why? Because the principle of relativity says the laws of physics are the same in every reference frame, and Einstein announced that it's a law of physics that light moves with a certain velocity. That is puzzling, and let's quantify and make precise why it's so puzzling. Let's try to be very, very almost pedantic about it. Let's start with a reference frame. A reference frame is a coordinate axis in space. Now, for our purposes now, space is just one-dimensional. I don't care about y and z. I care only about x. So let's draw an x-axis. Here's x. And also a time axis. Here's t. Let's call this your reference frame. And in your reference frame, light moves with the speed of light, with the standard speed of light. And so if a light ray is sent out from the origin, time t and x and position x, it will move with a trajectory given by x equals ct. That's the motion of the light beam. And what does that look like on this map here, on this map of space and time? It looks like a straight line. X equals ct. It looks like a straight line like this. Now, the faster the light moves, the closer to horizontal that line will be. In other words, in a given amount of time, the further it will move. So c is some number. If I actually put in 186,000 miles per second, that line would be practically so horizontal that you couldn't see the difference from horizontal. It would mean that this light ray goes 186,000 miles in only 1 second. That would be a very horizontal line. So I will use some other units for the speed of light. Units in which I can see explicitly that the light ray is moving. It moves a certain distance in a certain time. That's its velocity. Okay, now let's add a second reference frame. A second reference frame moving relative to the first. The second reference frame has an x prime axis. Its axis is called x prime, and the center of it, just like the center of me, is moving relative to you. So because it's moving, it means me, the center of my coordinate system, is moving also with a straight line. That's not a very good pen. Let's just try another one. Also moving with a straight line. And that straight line is x equals vt, where v is my velocity relative to you. Okay? So I'm moving with x equals vt. My position relative to you keeps increasing as a function of time, and that's the trajectory x equals vt. Now, I don't call this x equals vt. I just call it x equals 0. That's me. But I don't want to call it x equals 0. Let's call it x prime equals 0. That's x prime. I will agree that to call my coordinates primed. All right, I call my coordinates x prime and t prime. Next, what about, what's the relationship between your coordinates and my coordinates? Well, that's pretty easy. X prime is equal to x minus vt. This distance here is vt. My coordinate is called x prime. Your coordinate is called x. My coordinate is your coordinate less the distance between us, which is vt. So that's x prime equals minus vt. And what about our clocks? Well, if we make the assumption that Newton made the assumption that all clocks can be synchronized and that the time that a clock registers has nothing whatever to do with how it moves, then we can, before I even started to move, we could synchronize our clocks, and now I can start to move, and the rule will be my time is the same as your time. This would be the transformation of coordinates between your coordinates and my coordinates. If you know when an event happens, you can tell me and my coordinates when it happened. Okay, now let's take this light ray, the light ray that moves with x equals ct in your frame, and ask how it moves in my frame. All right, so I want to find out how the light ray moves in my frame. It's going to be x prime is going to be x, but along that light ray, x is equal to ct. All along this light ray, x is equal to ct. So that means along the light ray, x prime is equal to ct minus vt, which is the same as c minus v times t. So in my which is also the same as c minus v times t prime. That's important. That's important. So according to my watches and my clocks and my measuring sticks, that light ray, which was emitted from here, does not move with the speed of light c, but moves with the speed of light c minus v. That's bad. Something's wrong. At least if Einstein was right, something's wrong, because Einstein announced the rule that all light rays move with the same speed. Okay. What about a light ray going the other way, incidentally? The light ray going to the left would be x equals minus ct. If you plug that in to x prime is equal to x minus v t, you get x prime is equal to minus c plus v times t. In other words, a light ray going, if I'm moving to your right, a light ray going that way looks to me like it's going a little bit slower by this amount. A light ray going in the other direction appears to me to be going a little bit fast. All right. That was what Newton would have said, and that is what Galileo would have said, and it's what everybody would have said until the end of the 19th century, when people started measuring the speeds of light extremely carefully and found out that no matter how things were moving, the speed of light always appeared to be the same. The only way to reconcile this is to say something is wrong with the transformation law between your coordinates and my coordinates. Something is wrong with this simple-minded coordinate transformation here. So the first step of special relativity is to figure out how this has to change, your coordinates versus my coordinates, in order that the speed of light be the same in every reference frame. Okay, I'm going to take you through that first, through the steps. Even before that, we should go back and ask about perhaps assumptions that we made which were unwarranted. Well, there's a zillion assumptions we made, obviously, a lot of them. But the most important one, and the one which is most at risk, and in fact the one which is wrong, is that simultaneity in every reference frame is the same. That if we begin with our clocks synchronized, right, and now I start to move, will my clocks remain synchronized with your clocks? In other words, is this the right transformation between moving clocks and stationary clocks? And that, of course, in hindsight, is the one that we know was wrong, that the correct relationship is different, and in fact that the whole idea of simultaneity is frame dependent, is reference frame dependent. Here's what I want you to imagine. Each one of you has a clock, all right? Your clock, your clock, your clock. You synchronize them by whatever means you synchronize your clocks. I have an equivalent collection of friends who are spread out exactly the same way relative to me as the front row is here relative to this gentleman here. Each one of my friends has a clock. I've made sure that our clocks are synchronized, and now we're moving. We're moving relative to you. Okay? As we go past, we check each other's clocks, and we check whether they are synchronized, and if not, how much out of whack is each clock depending on how far down the line you are. Equivalently, we're asking, what is we could ask the same thing incidentally about our meter sticks. We could ask, as I pass you, is my x equals 1 unit of your position relative to you, if you get my point. And of course, this is where Einstein made the great leap. He said we have to be more careful. We have to be much more careful and define very carefully what we mean by synchronous and what we mean by lengths, what we mean by times. All right, so he said, okay, look, let me think about experimentally how I would synchronize two clocks. Given his postulate was the speed of light is the same in every reference frame. How do you go about synchronizing your clocks, and how should I go about synchronizing my clocks? I said, well, if light goes that direction with speed c and that direction with speed c in every direction, it will do a little trick. The little trick is if we have two clocks, let's say this gentleman at the end over here and that gentleman at the end over there, and they want to synchronize their clocks, they don't want to get up out of their seats. They're lazy. They don't want to get out of their seats. They want to stay where they're sitting. Then they find somebody right in the middle. Now, how do they know the person is in the middle? They measure with meter sticks. I'm afraid you'll have to get out of your seats if you want to do that, but you measure with your meter sticks, and you find that that's 5 meters or 4 meters to the center. You find that's 4 meters to the center. Go back to your seats, and now check your clocks. All right? So check your clocks by, we could also have somebody sitting in the middle there if we liked. We could check the clocks by when your clock reads 12 noon, and when your clock reads 12 noon, each send out a flash of light, a flash bulb. If the two flashes arrive at the center at the same time, then your clocks were synchronized. You each said you're going to send out your light beam when your clock reads 12 o'clock. If the light at the center arrives at the same time, then your clocks were synchronized. That's the way Einstein decided to define synchronicity. Now, what about me, me who's moving? I'm moving, I get to this point over here. When I get to this point over here, let's say that just happens to be the point that you emit your simultaneous light rays. All right? At 12 noon, according to your clocks, you each emit a light ray. But it doesn't quite get to the center at 12 noon. It gets to the center slightly later, according to your clocks, by which time I'm over here. Since I'm over here, your light ray will arrive at me a little bit late relative to your light ray. Okay? So I will say, you guys are out of synchronous. You made some mistake. You didn't synchronize your clocks because the light arrived at me at two different times. I can either say that, or I can say that the meaning of synchronicity is different in the two frames of reference. Okay, so let's go back to our two coordinate systems and be skeptical about exactly what synchronous means in the moving reference frame. In the stationary reference frame, we'll assume that synchronous means 2 points on the same horizontal, at the same horizontal level here. All right, at the same t. But what about the moving frame of reference? The moving frame of reference, we'll find in a minute that this point is not synchronous with this point, but is synchronous with some other point. And in fact, that the whole surface here, that the moving reference frame calls synchronous, not here, that's the wrong place, that's light. It's someplace else. We're going to map out what the moving observer calls synchronous. And how are we going to do it? We're going to do it by synchronizing the clocks according to Einstein's rule. Okay, so what we need now is a better drawing. Whenever you encounter a relativity problem, draw a picture. That's the first thing to do. You first draw a picture. The picture is always the same. It's x and t. X and t can be a reference frame that you can think of as stationary in your frame of reference. The other frame of reference, think of the railroad train moving down the axis. But the next thing to draw in, before you draw anything else, draw in light rays, how light rays move. So draw in x equals ct and x equals minus ct. In particular, x equals ct. We'll worry about x equals minus ct later. But as I said, if we were to use c equals 186,000 miles a second, we would draw a practically horizontal line. We don't want to do that. So we choose the speed of light in some units where it's easier to draw the picture. And in particular, the natural choice of units is to make the speed of light 1. All right. How do you make the speed of light 1? Well, you use length units, which are defined relative to your time units in an appropriate way. If your time units are seconds, use your length units to be light seconds. How big is a light second? Well, it's 186,000 miles, but never mind. 1 light second is a unit of length. And how fast does light go in units of seconds and light seconds? It goes 1 light second per second. All right? That means that on a diagram like this, where x measures light seconds and t measures seconds, light moves at 45 degrees. I'm sure you've seen this before, but I'm just spelling it out. It moves backwards at the same 45 degrees. All right, so that's the trajectories of light rays. Next, let's draw in another observer, another reference frame, a moving reference frame. And again, the reference frame is going to be moving x prime equals x minus vt. Exactly like it is here. Same picture, superimposed on the light ray. This is x equals vt. What is x prime along here? 0. This is also x prime equals 0. So let's put x prime equals 0. That's because x prime is x minus vt. And if x is equal to vt, x prime is equal to 0. All right? So that's the moving reference frame. And let's try to figure out where t prime is, where the t prime axis is. All right. We begin by putting in 3 people. The one on the end, the one in the middle, and the one at the other end here. All right, so at the initial time, right over here, we're going to put in a moving person. Not a stationary one. I should have said, not you people. My friends. My friends who are separated by equal distance. There's me, there's the one in front of me, and there was the one yet in front of him. Let's put in the first one. And he moves with the same velocity. That means moves parallel. Let's suppose that he's 1 unit ahead of me, but measured with your meter sticks. That means that this distance right over here is 1 unit. What does that say about the equation of this second blue line here? It says that it's x equals vt plus 1. It's 1 unit ahead in the stationary coordinates. What about the next person who's 2 units ahead? Like that. And his equation is x equals vt plus 2. Now, person 1 over here has a watch. And as it happens, his watch says time 0. What is time 0? That's not a time on my watch. I'll take time 0 to mean 12 noon. Time 0 occurs right over here along his trajectory. That's time equals 0. In other words, the moving observer and the stationary observer agree by assumption on what time t equals 0 means. The stationary observer, t equals 0 all along the horizontal axis. That's essentially the definition of the horizontal axis. All times from the stationary observer are the same along here. But let's see if we can figure out where time 0 is along this second axis, along, let's give these people names. Fred, Mary, and Seymour. Is that the way you spell Seymour? Yeah. All right. Fred, all right, so the way this is going to work now is at this point, Fred is going to send out a light signal to Mary. And at some point, I don't know what point yet, Seymour is also going to send out a light signal toward Mary, but they're going to send it in such a way that they arrive at Mary at the same instant. Okay? So, Fred sends out his light signal along here. Where does Seymour have to send out his light signal from in order that it arrive at exactly the same time? Well, if I start in this end and I start shooting light rays up at 45, I'm likely to miss this point. So I'll be smart. I'll work backward, 45 degrees to here. Each light signal in the stationary reference frame moves at 45 degrees. You can see, because the second reference frame is tilted relative to the first reference frame, that the point occurs above what the stationary observer calls t equals 0. This point over here, the moving observer will call t prime equals 0. Why? Because in the moving frame of reference, these 2 points sent light rays to the central observer over here that arrived at the same instant of time. So Mary will say, you guys sent me the light signal at exactly the same instant of time because it arrived at me at the same instant of time, and I happen to know that you're equally spaced. Now it just becomes a little exercise to figure out where this point is. So I'm going to take you through that exercise. I'm going to do it in detail. It's very easy. Let's give these points names. This is A and this is B. And what we want to figure out is what the coordinates of this point B are, because we know B is synchronous with the origin in the moving reference frame. That will give us some information. In other words, B must be a point, T prime, one of the points for which T prime is equal to 0. Okay, what about point A? How do we find point A? We find point A by recognizing that it's at the intersection of 2 lines. What is this line over here, the green line? That's x equals ct. This line is x equals ct because it's a light ray moving to the right. We've decided to set the speed of light equal to 1, or I decided. So it's really just x equals t. The motion of a light ray is just x equals t. And here's the light ray, that's this line. And the other line along there that this point A lies on is x equals vt plus 1. How do we find the intersection? We substitute one equation into the other, and it just says t is equal to vt plus 1. From the first equation, I just said x equal to t, or t times 1 minus v is equal to 1. Or, even better, t is equal to 1 over 1 minus v. All right, so we now know where the time of this point A is. This is point A. What about the x of this point A? I would like the full set of coordinates of this point. All right, so let's put a box around it. What's the x of that point? Well, you can write it as vt plus 1 and plug in what t is, but you can be smarter and you can say, look, this line is x equals t over here. The green line is x equals t. So all along the green line, x is equal to t. In other words, x is equal to 1 over 1 minus v. Now let's go to line AB. The next thing to do is to figure out line AB, which will ultimately figure out where it intersects x equals vt plus 2. It's a few steps. There's a few steps, but they're fun to do. So we'll go through them. And I don't know a shortcut for this. I don't know any shorter way to do this. What about the line AB? Okay, every line which is at 45 degrees but pointing downward to the right, in other words, 45 degrees but going upward to the left, is a line that has the property that x plus t is constant along that line. Every line moving upward to the right with 45 degrees is x minus t is a constant. Lines which are at 45 degrees but upward to the left are lines x plus t equals a constant. All right, let's take this one. It's x plus t is equal to something. What thing? Well, one easy way to find out what I should put on the right-hand side here is just to take one point on that line and plug in the value of x plus t. X plus t is the same all along this line, and in particular at point A, x plus t happens to be twice 1 minus v, 2 over 1 minus v. It's just this plus this, x plus t. So all along line AB, line AB, x plus t is equal to 2 over 1 minus v. So we've now found line AB. All right. We want to find point B. So there's one more step, and that step is to find the intersection of line AB with x equals vt plus 2. So we take x plus t equals 2 over 1 minus v, and we combine it with x minus vt equals 2. That's this equation over here. X minus vt equals 2. And we solve the two simultaneous equations, and that will tell us what the coordinates of B are. All right, so how do we do that? Well, the first step we can just solve by subtracting the two equations. That will get rid of the x. All right, so let's subtract. On the left-hand side, we have t minus vt, which means t times 1 plus v. That's equal to 2 over 1 minus v minus 2. All I've done is subtract. All right, I want to subtract 2 from a fraction, so the best thing to do is to put them over the same common denominator. T minus 2 times 1 minus v over 1 minus v. I've just multiplied and divided by 1 minus v. Okay. If you look at this carefully, you'll see the 2's cancel. 2 minus 2. The term with v here will become plus. This whole thing becomes twice v over 1 minus v. That's equal to t times 1 plus v. One more step to calculating t. It's just to divide by 1 plus v. So what happens if you divide by 1 plus v? Well, you divide by 1 plus v. 1 minus v times 1 plus v. Too many steps. I hate doing algebra on the blackboard, but I don't see any way around it. I could tell you to go home and do it, but... all right. What's 1 minus v times 1 plus v? 1 minus v squared, right? So we can just write this as 1 minus v squared and get rid of the 1 plus v. That's t. But it's not really t that I want. I want x and t at this point. So how do I find the x of point B? This is the t of point B. We could call it tb. What about the x of point B? Well, all I need to do is substitute into this equation. T is equal to tb, so let's see what it is. xb is equal to 2 divided by 1 minus v minus tb, right? I'm subtracting t from this equation, minus tb, and tb is 2v over 1 minus v squared. Looks ugly, but it's not. It's much...
When v is plus or minus 1.
What's that?
What happens when v is plus or minus 1?
Then bad things happen, right? Right. When v is plus or minus 1, that means that the observer here is moving with the speed of light, and we get into a kind of degenerate situation. Well, you just plug in. What does happen? Let's see. First of all, this one over here. When v is plus or minus 1, tb becomes infinite. So see what's happening when v gets to be plus or minus 1, let's say plus 1, this blue line is tilting over to become horizontal with the light curve. And not horizontal, parallel with it. And when it's parallel with it, they never intersect. So the intersection is at infinity. Right? Part of the game here, of course, is to realize that we will eventually disallow things moving faster or as fast as the speed of light. For the moment, it's a fair question, and something bad happens. So it begins to smell bad to have somebody moving with the speed of light. All right, we can simplify this. Multiply by 1 plus v in both the top and the bottom. Now use the fact that 1 minus v times 1 plus v is the same as 1 minus v squared, and we get everything over the same denominator. And let's see what we have. We have a 2v. We have another 2v with a minus sign. They cancel. And we just have a 2. The remaining thing is a 2. So it's not so bad. xb is equal to 2 over 1 minus v squared. The only difference between them is that there's an extra factor of v in tb. Now, why did I go to all that trouble? I went to all that trouble because I wanted to figure out where the surface, or the line, it's a surface in higher dimensions, where the surface, when there's also other space dimensions like y and z, where the line is which corresponds to being simultaneous with the origin here. And it's a line which passes right through that point. We could have found the other points in the line by using smaller or bigger intervals for the same argument. Same argument, but with smaller or bigger intervals. And we would have found that all the places which are simultaneous with the origin lie on the line which passes through the origin and which passes through the point B. What do we know about that line? We know that it has a constant slope. What is the slope? The slope, of course, is the ratio of t to x all along that line. And what's the ratio of t to x? It's just tb over xb, which is just v. The ratio of tb to xb is the ratio of this to this, and it's just plain v. That's all. So the slope of this line here is v. Another way to say it is that this line is t equals vx. T equals vx. All along this line, the moving observer says everything is simultaneous. So however moving clocks work, all the clocks along here, if they're synchronized, if they've been synchronized by Einstein's procedure, they will all read the same time. They will all read t prime equals 0 all along here. Right? Why? Because this operation here was exactly the operation to synchronize these two clocks. If this one reads t prime equals 0, so does this one, all along here. All right, now look at the diagram. Let me simplify the diagram. Let me make it get rid of a lot of the stuff on it. We have, first of all, a light ray moving at 45 degrees. We have x equals vt, that's the moving observer, the center of the moving observer. And then over here, we have t equals vx. Notice the symmetry of these two. X equals vt and t equals vx. The meaning of this symmetry is that this line over here is just the reflection of this line. They're just related by interchanging t and x, flipping about the green line here. Another way to say it is that they're at the same angle. This angle here is the same as this angle here on this diagram. So we've discovered something interesting. If Einstein is right, and if the speed of light is the same in every reference frame, and you use light rays to synchronize clocks, then what's synchronous in one frame is not the same as synchronous in the other frame. That's the first thing. And the second thing is we've actually found what synchronous means in the moving reference frame. It corresponds to surfaces which are not horizontal, but which are tilted a little bit, tilted by slope v. Okay. That solves the problem of what simultaneous means in different frames, and they're not the same. Okay, next. Can we say more about the relationship between xt and x prime and t prime? Let's, all right, we don't need this over, oh, we can just lift it up. Now, here's what we know. We know that x prime equals 0 whenever x equals vt. That x equals vt is the same as x prime equals 0. So let's begin writing x prime is equal to x minus vt. But we don't know that that's correct. All we know is that when x is equal to vt, x prime is equal to 0. This could be incorrect by some factor. Let's call it f. That factor could depend on the velocity of the relative velocity of the two frames of reference. So let's write f of the velocity between the two frames. And I mean the magnitude. How fast is it going? How fast is it going? The magnitude of the velocity. I use script v here to indicate the magnitude of the velocity. The velocity v can be positive or negative. The two reference frames could be moving, the moving frame could be moving backward, it could be moving forward, so v could be plus or minus, but the function that would go here, we might guess, is just a function of the magnitude of the velocity. Let's assume that for the moment. Okay. And that's the general answer for what x prime is, although we don't know yet anything about what the function v is, the function f of v is. What about t prime? Well, we know that t prime is equal to 0 whenever t is equal to xv. We knew that x prime was 0 when x equals vt. We know that t prime equals 0 when t equals xv. Just invert x and v. So it must be then that this is equal to t minus vx times some other possible function of v. These two equations tell us that x prime is 0 whenever x equals vt, and it tells us that t prime is equal to 0 when t equals vx. In other words, it's just reflecting this relationship that t prime is 0 when this is true, and x prime is equal to 0 when that's true. Okay, now we use some physics. We use the physics that Einstein said, that the speed of light is the same in both reference frames. What does that say? The speed of light is 1 in the stationary reference frame, so it must also be 1 in the moving reference frame. What that says is that whenever x equals t is along the green line, it must also be true that x prime equals t prime. If we have a light ray, and the light ray moves with velocity 1, this goes right back to the first thing that we demonstrated, that when we took a light ray that went like x equals ct, and then we transformed from one frame to another, remember what we got the first time around? We got c minus v and c plus v. All right, let's do the same thing now and say, supposing the light ray satisfies x equals t, then it must also be true that x prime equals t prime. How can we arrange that? Well, it's actually very easy. Let's suppose x equals t. Then, for that curve, we can write this as x times 1. Oh, let's write it. What do we have to do to make this equal to this when x is equal to t? If x is equal to t, these two will be the same. These two will be the same. So what's in the bracket here will be the same as what's in the bracket here when x is equal to t. If we want x prime to equal t prime, there's only one choice. That's to make f equal to g. That's the only way. Right? F must be the same as g. If f is not the same as g, the motion of the light ray in the moving coordinates will not be with velocity 1. So we come to the conclusion, Einstein's rule tells us that whatever the connection between these coordinates is, it involves the same function here What more do we know? What more do we want to know? We want to know what this function of v is. We would dearly like to know what that function of v is. Once we know it, we know completely how the coordinates in the two reference frames are related to each other. So we'll use one more ingredient. Incidentally, I'm practically regurgitating Einstein's first paper on the subject. I haven't read it for probably 50 years, but it has left, obviously, a very lasting impression on me. This is basically what he did in that first paper. Well, this and a lot more. Okay. So now he said, wait a minute, who's to say which frame was moving? Who's to say if my frame is moving relative to you with velocity v, or your frame is moving relative to me with velocity minus v? Whatever the relationship between the two frames of reference are, they should be symmetrical. We could take the entire argument, and instead of starting with the x and t and drawing in x prime and t prime, we could do exactly the opposite. The only difference would be that, as far as I'm concerned, you're moving with velocity minus v. As far as you're concerned, I'm moving with velocity plus v. So we can immediately write down what the relationship between x and t are in terms of x prime and t prime. Here it is. I'll write it down for you. Let's write it over here. It must be that x is equal to x prime. Now, what shall I write? Minus vt prime? Plus vt prime. Why? Because the velocity, the relative velocity has the opposite sign, times function of the same magnitude of the velocity. The magnitudes of the velocity, if I'm moving relative to you with velocity v, you're moving relative to me with velocity minus v. Let's assume this function is just a function of the magnitude of the velocity, which is the correct answer in the end. And t is equal to, what is it, t prime plus v x prime times same function of v. The question is, are these two equations, or these two sets of equations, compatible with each other? After all, I didn't really need to guess the relation between x and t over here. I could have just solved this equation for x, these two equations for x and t. Right? So I want to make sure that this equation and this equation are compatible with each other. I'm going to do it in a fancy way. Of course, that will determine what f is. The compatibility, here's the way you would do it. Here's the way you would do it. Here you have x prime and t prime in terms of x and t. Now supposing you take the x prime and t prime from here and plug them in over here, what will you get? You'll get x in terms of x and t in terms of x and t. How can that make any sense? It can only make sense if what you get is x is equal to x and t is equal to t. That's going to involve choosing f carefully. Okay, but I will show you there are more than one way to do this. Maybe we should just do it by plugging in. Yeah, let's do it by brute force. Let's just do it by brute force. I had a fancier way to do it. Okay, let's do it. X is equal to x prime, which is what? Somebody got to read it off to me. X minus vt times f of v. That's this guy over here. Then plus v times t prime, which is t minus vx, also times f of v, all times f of v, right? All times f of v, so that will square f of v here, right? Now, as I told you, the only way this can make sense is if it just reads x is equal to x. It's the only way it can make sense. And if I did the same thing for t, I would do the same thing for t here, plugging in t prime and x prime. And I'd better just wind up being t is equal to t. But let's look at it. What does it take? Let's combine things. We have x, x times f squared over here, x times f squared over here, and then we have plus v squared x times f squared. That's from here. And then what about the t dependence? Minus? Minus. But more important is the t dependence. The t dependence is minus vt here, minus vt times f squared. And here we have vt times f squared. This is minus vt times f squared. This is plus vt times. Good sign. The t's cancel automatically. Okay, we've done something right because the t's cancel automatically, leaving only the x's. And the x's have x times f squared minus v squared f squared x. Or in other words, x times 1 minus v squared times f squared. And that, by damn, has to be equal to x. How do we arrange that? Well, we arrange that just by choosing 1 minus v squared times f squared to be 1. In other words, it tells us what f has to be. And it tells us that f has to be 1 divided by the square root of 1 minus v squared. In other words, we cancel out the x, so we have 1 is equal to 1 minus v squared times f squared. F is equal to 1 divided by this square root. That's it. That's it.
But what about the other root?
That's probably some interchange of plus velocity and minus velocity. Let's see. So that would be minus. It sounds like it's an inversion of coordinates or something. It's probably an inversion of coordinates. I don't know, I never thought about it. Um, yeah, that probably corresponds to the possibility of reflecting the coordinates. X goes to minus x. It's a good question. I'm not sure what the answer is. Let's ignore it for the moment. It's got two roots. I'm not sure what it says. Okay, so now we have the answer. Oh, I know what the answer is. Okay. Square root of 1 minus v squared over square root of 1 minus v squared. All right, now I'll tell you what the answer is. First of all, which root you pick, plus or minus, should not depend on the velocity. There shouldn't be some point in velocity at which you suddenly jump from one root to the other root. That would be a very discontinuous thing to do as a function of the velocity. So you say, what do I know? Well, what about for velocity v equals 0? Certainly for velocity v equals 0, in other words, when the two frames are not moving relative to each other, we want the two frames to be the same. So that says that x prime equals x, not x prime equals minus x. The two roots here would correspond to the two possibilities, x prime equals x or x prime equals minus x. Surely, when the frames of reference are at rest relative to each other, we want the solution to just be x prime equals x and t prime equals t. So that says pick the positive root, plus square root of 1 minus v squared. Okay, let me write this more completely. Let me write it again. Let's write it the usual way. And I assume you recognize this. T prime is equal to t minus vx over square root of 1 minus v squared. Notice they have the same form except x and t interchanged. X prime is x minus vt, t prime is t minus vx, all divided by square root of 1 minus v squared. Okay. These are, of course, the Lorentz transformations. These are the Lorentz transformations, and they've been cooked up to make sure that in every frame of reference the speed of light is 1. Okay. What do you do if the speed of light has not been chosen to be equal to 1? What if it's just c, where c is whatever you choose it to, however you choose your units? Then, to figure out what's going on here, all you have to do is say, well, if I'm going to use other units, I must have these equations be dimensionally consistent. I must have these equations. Now, velocity is a length over a time. Well, an x is a length, a time is a time, this is a length over a time, so the numerator here, the two terms are consistent with each other. That's fine, no problem. But what about the square root of 1 minus v squared? The units of 1 are just 1, they're dimensionless. The units of a velocity are a length over a time. So and that does not have units 1. So this velocity squared here must not really be velocity squared. The only way to make it dimensionally consistent is to make this v squared over c squared. In other words, had we kept the speed of light in everywheres, this v squared really would have meant the velocity in units of the speed of light. By setting the speed of light equal to 1, equivalently, we said velocities are measured in units of the speed of light. V equals a half would mean half the speed of light. Okay. So the only way to restore the dimensions and get the dimensions right in this equation is wherever you see v squared, put v squared over c squared. Now this equation is not quite right. What's wrong with this equation? The left-hand side is a time. The denominator is okay. The right-hand side starts with a time, but is v times x a time? You need to divide by c squared. V is a length per unit time, but if I multiply that by a length, I get a length times a length over a time. That doesn't sound right. So this v must be v over c. A simpler way to say it is the way I said it a moment, v over c squared. Yeah, v over c squared. Right, v over c squared. That's the only way to restore the units. And now this is the recognizable Lorentz transformations. Notice that as long as the velocity is very small compared with the speed of light, so that v squared over c squared is even smaller. If v is a tenth the speed of light, v squared over c squared is 1/100th. If v over c is 10 to the minus 4 or 10 to the minus 5, this v squared over c squared is truly a small number. And the square root just becomes 1. What do we get? We get x prime is equal to x minus vt. That's the good old Newton version of things. What about the second equation here? If v over c is very small, in other words, let's now plug in some numbers. Supposing v is 100 miles an hour. Let's even make it bigger. Let's make it 100 miles a second. C is 186,000 miles a second, and c squared is enormously big. So v over c squared is a very, very tiny number. And so this term here, if the velocity of the reference frames is relatively slow, this is negligible. Also, 1 minus v squared over c squared. This is negligible. Therefore, the rule is t prime equals t. For reference frames moving slowly relative to each other, it's just the good old Newtonian type formula. All right. This goes away. This goes away. V over c squared is negligible. In other words, wherever you see c in the denominator, ignore that term because it's just too small to count. So this is good. As long as we're moving slowly compared to the speed of light, we get the old answer. But when we get up near the speed of light, there's huge corrections. When we get up near the speed of light, big things happen. Okay, those are the Lorentz transformations, which I assume you've seen before. You may have even seen the derivation before. Incidentally, what happens to y and z, the other components of space? Now, we've been very specific in talking about a frame of reference moving along the x-axis. The motion, the relative motion of the frames is along the x-axis. But what happens to the y direction when you do this? Well, physically, what does it mean? If your arm was the same length as my arm, stick your arm out, okay? Stick your arm out. And we went past each other. The question is, when we met at this point, would our arms match? Or would yours be longer than mine? Well, just by symmetry of the problem. We could either refer to somebody sort of moving halfway between us, or it's clear that our arms are going to match, because there's no reason for one to be longer than the other. Okay. So therefore, the rest of this Lorentz transformation would involve y prime equals y and z prime equals z. In other words, things only happen in the plane, the xt plane, where the motion is along the x-axis. X and t get mixed up with each other in this funny way. Y and z are just passive. They don't do anything. They just stay the same. Your y and my y are the same no matter how fast we're going, but our x's and t's get mixed up with each other in this way. That's special relativity. Let's talk very briefly about time dilation and space contraction. While we're at it, we might as well do it. We have all the ingredients we need. I'll just do a couple of illustrations. Again, draw a picture. Let's first talk about what we're doing. I have a meter stick and I'm walking past you. Or do I want you to be the... No, you're the one to hold the meter stick. You hold the meter stick. You got the meter stick? Hold it there. All right? Right. Now, you know that that's a meter. I walk past you, and as I walk past, I ask, how long is your meter stick? Right? I measure it relative to my meter sticks. But I have to be very careful what I mean by that. In particular, since I'm moving, if I'm not careful, I will be measuring the endpoints of your meter sticks at different times. In fact, I want to be measuring the endpoints of your meter sticks at a common time which is synchronous to me. Why do I want to do that? Because that's what I mean by the length of your meter stick in my reference frame. I mean the length of your meter stick relative to my meter sticks, where the two endpoints of your meter sticks are examined at the same time in my reference frame. That's the definition of what I mean by the length of your meter stick. That I look at the endpoints of your meter sticks at a common instant of time, and I measure the distance between them with my measuring rods. So let's draw a picture to indicate what that means. The meter stick is at rest in your reference frame. It goes from x equals 0 to x equals 1 meter. Here's one end of the meter stick, here's the other end of the meter stick. Of course, they exist at all times. They're standing still, and so the meter sticks are just vertical. The ends of the meter sticks are just vertical lines here. Now I want to know, in my moving reference frame, so again, we draw in the moving reference frame. This is t prime equals 0. Here's t equals 0. This is x prime equals 0. This is x equals 0. And what do I want to know? In my moving reference frame, here's one end of the meter stick as I pass it right over here. Here's the other end of the meter stick at time t prime equals 0. Not at time t equals 0, but in my moving reference frame, I say that this is the two ends of the meter stick at time t prime equals 0. What do I want to know? I want to know what x prime is at this point. I want to know what x prime is at that point, at the point t prime equals 0. Well, this is not hard to figure out. First of all, let's see, t prime, let's go back and set the speed of light equal to 1. I don't want to carry around the speed of light. Here's the Lorentz transformations. And let's look at this point right over here and see if we can figure out what its coordinates are. It's x equals 1 and it's t prime equals 0. X equals 1, t prime equals 0. So t prime equals 0 means that t equals xv. Right? This surface is t equals xv. All along here. So that's the first thing I know. I know that t is equal to xv, and I also know that x is equal to 1. So let's see if we can find out what x prime is. X prime is equal to x, which is 1, minus vt, but t is equal to xv. Everybody got the logic? The logic is a little bit slippery here. Let me go back to it. We're trying to figure out what the moving observer ascribes to this point at the other end of the meter stick at an instant of his time. So we try to figure out what the coordinate x prime is at the end of the meter stick. What do we know? We know that t prime is equal to 0 over here, and we know that x equals 1. So we use the Lorentz transformations.
Shouldn't x prime equal 1?
No, this is the meter stick at rest. The meter stick is at rest, your frame.
So it's being measured from the moving frame?
Yes, we're trying to measure it from the moving frame, which means we're trying to find out what x prime is over here. So we have two pieces of information. One is that t prime is equal to 0, the other is x equals 1. First step, use t prime equals 0. T prime equals 0 tells us that t is equal to Vx. All right? So t is equal to Vx. We're trying to find x prime, so it's x prime is equal to x, which is 1, minus v times x, v squared x, divided by square root of 1 minus v squared. Okay? X, that's just equal to 1. In fact, I don't even really need to say it's equal to 1. I could just say it's x. But let's just say it's x equals 1. And so what do we find? We find that x prime is equal to 1 minus v squared over square root of 1 minus v squared, which is just equal to square root of 1 minus v squared. So the moving observer says that at an instant of time, meaning to say along this surface of synchronous times here, the two ends of the meter stick are separated in his frame, or in the moving frame, by a coordinate distance or number of meters in the moving frame, which is given by square root of 1 minus v squared. In other words, the meter stick looks in the moving frame of reference to be a little short. To look a little short compared to what it was at rest. Notice, though, that they're really talking about two different things. The meter stick at rest, we're talking about the distance between this point and this point as measured by stationary meter sticks. In the moving frame, we're talking about the distance between this point and this point measured by moving measuring rods. They're not really the same point of space and time here, so there's no real contradiction that one looks shorter than the other. You can do the other calculation. The other calculation, I'll leave it to you. Here's the way the other calculation, the sort of opposite calculation. Think of the moving meter stick now. Here's the moving meter stick. If it's 1 unit long, what do we know about this line here? Is it x equals 1? No. It's a meter stick, 1 unit of length in the moving reference frame. That means it's x prime equals 1. In the moving reference frame, it is 1 meter ahead of the other end of the meter stick, of the tail end of the meter stick. And so it's x prime equals 1, not x equals 1. And now the observer at rest sees the meter stick, the moving meter stick, being this long. So he has to calculate what this point is. What's x at that point? You can do it, and you'll find out that it's also shortened by square root of 1 minus v squared. The moving meter sticks look short to the stationary reference frame. The stationary meter sticks look short to the moving reference frame. Okay? There's no contradiction. They're just talking about different things. The stationary observer is talking about lengths measured at an instant of his time. The moving reference frame is talking about lengths at an instant of the other time. So they're talking about different kinds of things. Different notions of what they mean by length, yeah.
So you say the meter stick looks shorter.
Well, no, forget look. Let's be very precise about it. I hold my meter stick and I move with it. And at some instant of time, remember, you people have synchronized your clocks, okay? So at exactly 12 noon, somebody is going to see the tail end of my meter stick pass them, and somebody else is going to see the front end of the meter stick move past them. Right? So they've got their watches synchronized, and they've instructed each other at exactly 12 noon, see who along here is contiguous or adjacent to the two ends of the meter stick. And then after you've done that, compare notes and say how far apart were you. That's exactly what you mean. Forget saying that it looks shorter. You mean something very specific. with synchronized watches and synchronized clocks, just ask exactly where the ends of the meter stick were in your reference frame at an instant of your time. Okay? I can do exactly the same thing. I have all my buddies lined up. They also have clocks. We've also done the synchronization. My synchronization is not the same as your synchronization, but we've done our synchronization. You hold, who was holding the meter stick before? I was holding the meter stick a second ago. Now one of you people is holding the meter stick, and I march past, and I instruct all my people at exactly our time, 12 noon, look at the stationary meter stick and see how far apart the ends are. In both cases, they will look a little bit short from the frame of reference in which the meter stick seems to be moving.
Because if they didn't look the same from each perspective, it would imply an absolute reference frame.
It would indeed, but since we've established and made sure that the relationships between x's and t's and x primes and t primes are essentially the same relations, except with v goes to minus v, we know that that can't happen. The mathematics of each half of it will look exactly the same as the previous one. So you can go through it, check this out. The last thing to talk about before we move on to the motion of particles.
Quick question.
Yeah.
This isn't a meter stick, is it? Because our units aren't meters.
What's that? Say it again.
It's not a meter stick because our units aren't meters.
It's a light second stick.
You mean this is not a meter?
Yeah, because we're assuming c equals 1.
Oh, indeed. Well, of course, well, it depends on our choice of time. You could use for time the time interval that it takes light to go 1 meter. But then we, right. Yes, you're right. You're right, but I'm also right. Good. Okay. Yeah, you're right. What about time dilation? Time dilation, we can pretty much work the same way. Supposing we have a moving clock. Supposing we have a moving clock, and for the moment, I'm going to assume my clock is moving with uniform velocity. In particular, we have a clock that's moving with the moving observer. My clock, I'm moving, and my clock is right sitting on top of me. It's not one of my friend's clocks, it's my clock, and it is moving along a trajectory like that. Okay. Here's the question I want to ask. At the instant when my clock reads to me personally, when it reads t equals 1, let's say. Maybe it could be a little more general. No, let's say t equals 1. When it reads to me, t equals 1, the question is at that point, what is the time in your reference frame? Right? So when I say t equals 1, do I mean t equals 1 or do I mean t prime equals 1? My coordinates are t prime. So I have my clock. It's my standard wristwatch. It's been made in the Rolex company. It's a good watch. It works well. The guy sold it to me for $25. And
Has to go to New York.
I got it in New York, right? I got it in New York from a guy. He said, right. It works well. So it's t prime equals 1. 1 second, though, 1 unit. T prime equals 1. And I want to know what the corresponding value of t is all along the horizontal surface. The horizontal surface is the surface that you call synchronous, that you call an instant of time. All right, now what else do we know? We need 2 things in order to pin down this. We also know that x prime is equal to 0, huh? X prime is equal to 0 all along here, and t prime is equal to 1. Let's see if we can find out what t is. All right, so we write our Lorentz transformations. X is equal to x minus vt over square root of 1 minus v squared. I don't think we're going to need that one. And the other one is, oh, I'm sorry, this is not the one we want. We want the other one, which goes x is equal to x prime plus vt prime over square root of 1 minus v squared. And t is equal to t prime plus vx prime over square root of 1 minus v squared. I simply used the other form of the Lorentz transformation where I write x and t in terms of x prime and t prime, and to do it, I've replaced v minus v by minus v. Okay. So this is the other Lorentz transformation going the other way, telling me the x and t coordinates in terms of x prime and t prime. Okay, so t prime is equal to 1, x prime is equal to 0, and what I want to find out is t, that's right over here. Let's see what it is. T prime is equal to 1. X prime is equal to 0 divided by square root of 1 minus v squared. Right. So the time over here, is it bigger or smaller than 1? Bigger. Bigger. The time interval over here is longer than the time interval measured by the moving observer by a factor of square root of 1 minus v squared. This is the origin of the twin paradox. The twin paradox involves reversing the motion of the twin over here, two twins, one at rest, one moving, reverse them, bring them back together again, and ask how much time has evolved in the two reference frames. Well, one of these reference frames is not an inertial frame, the one which bends and goes around. But we've already calculated how much time there was between here and here. That's 1 over square root of 1 minus v squared. In other words, we found that there's a little bit less time along here than along here. Same thing is true for the second leg of the journey. The implication is that the time measured in the moving frame is a little bit less than the time measured by this factor in the frame of reference of the twin that stays at home. And so the twin that stays at home is a little bit older than the one who moves. We're using here a basic idea that every clock participates in this thing in exactly the same way, and in particular the clock that has to do with biological aging also slows down. But this is just a statement that, you know, whatever we've said here applies to every kind of clock, not just Rolexes.
I had a hard time accepting.
What's that?
I had a hard time accepting hypotenuse is shorter than one of the sides.
Let's say it again. I can't hear you.
I have a hard time accepting the hypotenuse being shorter than one of the sides.
Yes, isn't that interesting? We're going to come to that. Yes, that's right. That's exactly right. No, it's not right, but I mean it's exactly something that that you might be puzzled by. So now let's talk about exactly that. Let's talk about exactly the issue of the hypotenuse and whether it's shorter or longer than the sides of the yeah.
You were saying that the twin that goes away and comes back, less time has passed for him. Mm-hmm. But from his point of view, we flew away. No. Remember, these two frames are not symmetrical with respect to each other. One of them underwent an acceleration. They're really not symmetrical. The twin who got sent out and sent back knew that he was the one who went on the curved trajectory because he experienced an acceleration. It was not, that twin was not in an inertial frame. So is that the cause then, is because the acceleration that,
You can think of it that way. You can just calculate it, or you can think of it as the cause of the acceleration, if you like. That's a legitimate way to think about it, right? But you know, the mathematics is pretty similar to the statement that if you take 2 points in the plane, ordinarily just 2 points in the plane, and you connect them by a straight line or you connect them by a curve, don't be surprised that the length along the straight line is not the same as the length along the curve. In fact, the length along the curve is, of course, longer than the length along the line. And in the relativity case, we actually found that the time along the curve was a little bit less than the time along here. So there's something going on that's different than ordinary lengths, but it's a similar phenomenon that that the length along a curve is not the same as the length along the straight line. The straight line is the shortest distance between 2 points. Well, in fact, in relativity, we've erased the diagram. Did I erase it? Yeah, here it is. As was mentioned, the time along the hypotenuse is less than the time along the vertical axis here. So there's something funny going on, and I want to talk about that funny thing that's going on. Let's just think about Euclidean geometry for a minute. Think about the plane, and let's think about different coordinate systems on the plane. Coordinate systems just related to each other by rotation. Now, there's an origin of coordinates. Let's call this x and y. This is now x prime and y prime. This is not a moving reference frame now. This is just the rotation of coordinates, and I'm using it to make a point. But let's take a point somewhere in the space over here. It's the point xy. The two reference, well, let me call them reference frames. I really mean coordinate systems. The two coordinate systems do not ascribe the same values of x and y to this point. Obviously, the x and y of this point here are not the same as the x prime and the y prime. They're related to each other. If you know x and y, and you know the angle between the coordinates, you can figure out x prime and y prime, but they're not the same. But there is something that is the same, no matter how you calculate it, whether you calculate it in the primed coordinates or the unprimed coordinates. And you know what it is. It's what? The distance from the origin. Everybody will agree on the distance from the origin. In fact, they'll also agree about the square of the distance from the origin. So what is the square of the distance from the origin from the point of view of the unprimed coordinates? Well, it's just Pythagoras' theorem. It's just x squared plus y squared. That's the square of the distance. What about from the point of view of the primed frame? In other words, the quantity x squared plus y squared for a point here is an invariant. Invariant means that it doesn't depend on which coordinate system you work it out in. It's invariant under changes of coordinates, which in this case are just rotations of the coordinates. So we say then that x squared plus y squared is an invariant quantity, and it's the same no matter what frame you measure it in. Question, is there an analogous quantity associated with the Lorentz transformations here, which is invariant? In particular, here's something we might guess. Let's try it out. Let's try it out and see if there's something similar going on in Tx space. Here's T, here's X. This point is characterized by a T and an X, but it's also characterized by a T prime and an X prime. It has a T and an X, or a t prime and an x prime. It has coordinates in the unmoving frame and the moving frame. What is the relationship between them? It's the Lorentz transformations. But we might guess, we might ask, is there something similar that's invariant? Right? Let's make a guess that it's t prime squared plus x prime squared equals t squared plus x squared. Let's try that out and see if it's true. We know in terms of x and t, we know x prime and t prime, so we can work it out. Let's see if it's true. Okay, so t prime, let's start with t prime squared. We just take this equation over here. T prime squared has, it has t squared, it has plus v squared x squared, and it has minus 2 vtx divided by 1 minus v squared. Did I do that right? That's t prime squared. What about x prime squared? That has x squared plus v squared t squared minus 2 vtx, right? Question, does this equal t squared plus x squared? Hell no. It does not. And in particular, one thing you can see immediately is that the xt term here adds to the xt term here. They do not cancel. There's no xt here. They can't be the same in general. And they're not the same. They're simply not the same. But now if you look carefully at it, you might notice that if we subtract them, the vtx terms do cancel. Okay, let's see what else happens. So let's try subtracting them. This is t prime squared minus x prime squared. And let's not prejudice by what's on the right-hand side here. Let's find out what's on the right-hand side. T prime squared minus x prime squared is this difference. All right. It contains the cross term here disappears. They cancel now because of this minus sign. And how about x squared? Let's see what x squared has. X squared has v squared minus 1, right? V squared minus 1. And then there's plus t squared. And t squared has 1 minus v squared. 1 minus v squared, all divided by 1 minus v squared. The 1 minus v squares cancel, and you just get t squared minus x squared. This is minus, minus, plus. Okay, so we've discovered something. We've discovered that there's an invariant quantity under any Lorentz transformation. The combination t prime squared minus x prime squared is the same as t squared minus x squared. It's almost like Pythagorean theorem, that there's a kind of notion of distance from the origin here, which is composed out of the base of the triangle, namely x, and the height of the triangle, that stays the same if you do a Lorentz transformation. In other words, if you use other coordinates, calculate x prime and t prime, you find out that the combination t squared minus x squared is the invariant. You can also take it to be x squared minus t squared, incidentally. X squared minus t squared and t squared minus x squared. Take your choice. Okay? This is an important thing to know. It's very important to know what the invariants are. The components of a vector or the components of a displacement are not invariant. They depend on which coordinate system you're using. The things which are invariant, things which all observers agree upon, are, in this case, I'll give it a name in a moment. Let's call it the space-time distance. The space-time distance, which is defined with this funny minus sign, is invariant, all observers, so it must be an important quantity. Okay, let's see if we can figure out what it really means. In particular, let's suppose that between here and here, that we happen to be talking about the motion. In other words, let's just assume, let's take a special case. Yeah. Let's take the 2 points to be along the motion of a moving observer. Okay? All right. Then, for this moving observer, what is t prime squared minus x prime squared? Well, x prime at this point is just plain 0. This is the point x prime equals 0 along here. So it is just t prime squared. In fact, we can write immediately that t prime squared must equal t squared minus x squared. Why do I say that? This point over here is the point t prime and x prime, but it's x prime equals 0. So its distance from the origin, t prime squared minus x prime squared, is just plain t prime squared. On the other hand, because this quantity is invariant, it must also be t squared minus x squared. What is this quantity t prime? It's the reading of a moving clock. A clock moving along here, which starts at t prime equals 0 over here, will read t prime over here. That's what it is. It's the reading of a clock that has moved on a straight line between one point and another point. It's how many units of time have occurred in the frame, in the frame that connects these 2 points. It's called proper time. It's called the proper time, and everybody will agree on what the proper time is along that trajectory. They will calculate it the same way. They will take the 2 points and calculate the square of the difference of the time interval between the 2 points and the space interval between the 2 points in any frame whatever. You pick your frame and you calculate t squared minus x squared for this point, and that tells you how much time evolved between the clock reading over here and the clock reading over here. It's called the proper time of that clock. But you can also just think of it as a measure of distance along a line connecting 2 points. It's not a measure of ordinary distance, it's a measure of space-time distance, called the proper time. It's this minus sign here which gives the triangles the peculiar property that the hypotenuse is shorter than the height of the triangle itself. Why is that? The minus sign makes it smaller. The minus sign makes it smaller. All right, but in many other ways, this functions as the notion of a distance in space-time between 2 points. Are there any questions about that? Yeah.
So up there where we actually drove the Lorentz transformations, we used...
Drove?
Some kind of a transformation, I'm not sure what. We used angles and slopes and matched coordinates, but what this is saying is you can't do geometry, at least not
No. Right, but we never used any notion of lengths in this. We just used coordinates. We never really, yeah, that's right. You can't use ordinary notions of Euclidean geometry on space-time. But still, we were very careful and simply defined coordinates in terms of how clocks would read, and we drove the invariant. We drove the invariant, and that's it. That's the invariant. Right. So relativistic space-time is kind of like ordinary Euclidean space-time, but with a funny difference that you take the difference between t squares and x squares, and that's the thing which everybody will agree on. And you can think of it as a kind of length. Now, there is one funny property of it. What about the points? Let's take the point. Let's go back to this here. Let's take one point at the origin, and let's take some other point. We can just use x and t. Let's just use x and t now. X and t. Another point at x and t. Is it possible that the distance between these 2 points, and these are different points, this one's at the origin, this one's not at the origin, is it possible that this notion of distance just gives 0 distance between them, even though they're not the same point? In ordinary Euclidean geometry, if the distance between 2 points is 0, the points are at the same place. Right? Good. What about in this crazy kind of geometry with the minus sign? Supposing the distance from this point to the origin is 0. What does that mean? That means that x squared minus t squared is equal to 0. All right, x squared minus t squared can be equal to 0 without x and t being 0. Incidentally, x squared plus y squared equals 0 implies that both x and y are 0. Right? X squared is positive, y squared positive or 0. Y squared is positive or 0. If the sum of these is 0, it means either one of them, both of them have to be 0. But if x squared minus t squared is equal to 0, it doesn't say any such thing. What does it say? It says either x is equal to t or x is equal to minus t. One or the other. X is equal to minus t. One or the other. What does x equals t mean? It means a light ray. It means that a light ray could go from this point to that point. They're connected by a possible light trajectory. Same for the other one. X equals minus t would be over here. Again, light ray can go from one to the other. So one of the facts here is that if the distance between 2 points is 0, it doesn't mean the 2 points are the same point. It means that a light ray can connect them. Still, nevertheless, it does mean that the proper time between the two of them is 0. In other words, if a light beam could carry a clock with it, there would be 0 ticks of the clock between here and here. Clocks that move with the speed of light simply don't tick. They just stick. They don't tick. Right. Yeah.
Could proper time just as well be called proper length?
Well, okay. Yeah, no, that's a good question. That depends on whether the 2 points, all right, here are 2 points which could not be the path of a moving object, of a clock. Why? Because the velocity, in order to go from here to here, would have to be greater than the speed of light. Okay? If we assume nothing can go faster than the speed of light, then this can't connect these 2 points. That's the condition, basically, that x is bigger than t. Here, x is less than t. If x is less than t, a light ray can get from one point to another. If x is bigger than t, it can't. If we're talking about 2 points in this type of configuration, they're called, and there's a word for it, they're called, the relation between those 2 points is called space-like. Space-like means that the space component is bigger than the time component, or better yet, that x squared plus x squared minus t squared is greater than 0. If the point is up here, so that a trajectory can connect those 2 things, then t squared minus x squared is greater than 0. This is called space-like, this distance, and this one is called time-like. If the 2 points are space-like connected, then you would call this quantity x squared minus t squared, you would call the proper distance between them. If they're time-like separated, then you would call t squared minus x squared the proper time. So yeah, you can think of it also as defining a proper distance, but only if the t component is larger than the x component. All right, we're close to the end. There's only one for today. I was going to talk about some relativity paradoxes, but I don't think we have time today. what was the other thing I wanted to mention? I've forgotten. Are there any questions? Yeah.
If the velocity of light is not 1, do we have to put C's in that equation? Those equations?
Oh, yes, absolutely. So, okay. So where would you put the C in this equation? We could put it here, C squared T squared, or we could put it in the denominator here. A distance divided by a velocity is a time, so this would be, and this would normally be called proper time, as units of time. If we go up to x squared minus t squared, and we put the c squared here, we would call this proper distance. Okay, but that's a pure convention. It doesn't matter where you put the c squared, whether you put it here or here. Just make things consistent. The definition of proper time is usually taken to be t squared minus x squared over c squared.
B square root?
Where square root where?
Because the units for that would be time squared, but for proper time, would that be blue and
Oh, sorry, proper time squared. Yeah, proper time squared, thank you. Right, that would be proper time squared. Yeah, it's square, it's like the Pythagorean theorem. The notion of distance is to take the square root of this thing. Most of the times you don't take the square root, but yes, the proper time is the square root of t squared minus x squared. Thank you, that's important. Yeah.
Is it useful to think of the Lorentz transformation as a rotation?
Well, yeah. The trouble is it's a rotation by an imaginary angle. Imaginary in the sense of imaginary, yeah. It is literally a rotation by an imaginary angle. So yes, it is sometimes useful to think that way. Right.
At the beginning, you mentioned that Einstein added the fact that C was a law of physics. Was that to match the experimental data at the time, or was
Who knows?
Okay.
Well, you know, I know the history a little bit. Of course, I don't know the history. I know the history is told by a participant. I didn't know the participant, of course. All right, I think there's every reason to believe him. I think Einstein was motivated by Maxwell's equations. He took Maxwell's equations to be a law of physics. Now, he was only 16 years old at the time when he started thinking about it, according to himself. He was 16 years old, and what he knew about Maxwell's equations was that they gave rise to these wave-like solutions, and that the solutions moved in a certain way. And he was puzzled because he tried to figure out what would happen if you moved along with a light ray. Then you would see a static electric magnetic field that had a wave-like structure that didn't move, and he knew somehow that that was not a solution of Maxwell's equations. So according to him, that was the motivation that he was puzzled by the idea of moving along with the speed of light, the light ray. But I think beyond that, he knew Maxwell's equations, or at least at some point he learned Maxwell's equations, and took Maxwell's equations to be laws of physics. And Maxwell's equations say light moves with the speed of light. So I'm inclined to believe that that was the correct history, that he didn't know at the time the Michelson-Morley experiment, but who knows? I mean, you know.
Oh, he didn't know about it. That's what you just said he didn't know about Michelson.
According to his own historical testimony about it, he did not know about it. I think there's every reason to believe he was surely smart enough. I mean, the logic makes sense that Maxwell's equations, you know, in modern terms, we would say it differently. We would say, here are these Maxwell equations, and there's some symmetry of the Maxwell equations, some set of coordinate transformations for which, if you do them, Maxwell's equations have the same form in every reference frame. if you take Maxwell's equations, which contain x's and t's, okay, and you plug in, you know, the old Newton rule, or the Galileo rule, x prime is equal to x minus vt, t prime is equal to t, you'll find out that in the new primed frame of reference, Maxwell's equations change their form. They don't have the same form that they had originally. If you plug in the Lorentz transformations, you find out that the Maxwell equations in the new coordinates are identical to what they were in the old coordinates. So I think in modern language, I think what Einstein did was to recognize that the symmetry structure of Maxwell's equations was not these transformations, but these transformations. But it was all encapsulated in one principle. He didn't have to really know Maxwell's equations. All he had to know was that Maxwell's equations were a law of physics, and the law of physics said that light moves with a certain velocity. And from there, he could just work with the motion of light rays. So, yeah. I mean,
Lorentz, they're called Lorentz transformations.
Lorentz-Fitzgerald transformation.
So he presumably had thought of them earlier for some other purpose.
No, he thought about them for the same purpose. He did know about the Michelson-Morley experiment, but he envisioned them differently. Same equations, but he envisioned them differently. He envisioned them as effects on moving objects caused by their motion through the ether. So he envisioned that an object moving through the so-called ether, because of various kinds of ether pressures, would be squeezed and therefore shortened. Now, was he wrong? I suppose you can say in some way or another that he wasn't wrong, but he certainly didn't have the vision that Einstein had of a symmetry structure, of what is the symmetry required of space and time in order that it agree with the principle of relativity, of the motion of the speed of light. Nobody, I think, would say that including Lorentz, would have said that Lorentz did what Einstein did. And furthermore, Lorentz didn't think it was exact. He thought it was a first approximation, that a thing moving through a fluid of some kind would get shortened, and that the first approximation would be the Lorentz contraction, and in some higher orders you would see some other things happening. So he fully expected that the Michelson-Morley experiment was not exact. He thought that there would be higher corrections to higher powers of velocity over c, where you would see discrepancies. Now, Einstein said, look, this is really a law of physics. This is a principle. So he made a principle out of it. And not likely to go away. Even in Italy. Good. All right, next time we'll talk about the motion of particles and how relativity helps you understand how particles move and things of that nature.
For more, please visit us at stanford.edu.